Hello and welcome to Sleepy Ocean. I'm really glad you're here tonight. Maybe you're the kind of person who likes to think their way into sleep, to let your mind drift towards something vast and quiet, something that makes the ordinary weight of the day feel very small. Tonight, we're going to the bottom of the world, not in any frightening sense, just in the way that the ocean goes deep and deeper still, and keeps going long after the light has disappeared entirely. The Tonga Trench sits in the southwestern Pacific, and it holds some of the most quietly remarkable facts on the planet. You'll hear about a seafloor that moves faster than your fingernails grow. Considerably faster, actually. You'll hear about water pressure so immense that it changes the chemistry of the sea itself. And you'll hear about creatures that have never seen light, going about their lives in the dark as they have for millions of years. Go ahead and get comfortable. If you haven't already, let your body settle into wherever you're resting. Take a breath in and let it go slowly. There's nowhere to be. The trench has been there for tens of millions of years, and it will wait for you. The Tonga Trench is the second deepest place on Earth. It descends to roughly 10,800 meters below sea level. That's 10.8 kilometers of open water above a seafloor that almost nothing has ever visited. To feel that depth another way, if you stack two Mont Blancs, the tallest peak in the Alps, directly on top of each other, the combined height would still fall short of reaching the surface from the bottom. The trench runs for about 2,500 kilometers, curving gently through the southwestern Pacific, like a slow scar pressed into the ocean floor. It is not a crack so much as a consequence. The shape left behind when one enormous slab of the earth slides beneath another. The Pacific Plate presses into the Tonga subduction zone at roughly 24 centimeters per year. That is about 24 centimeters every 365 days, which works out to more than 2 millimeters per week, steadily, without pause. For a tectonic plate, this is a sprint. Most plates drift at something closer to the rate of fingernail growth, but the Pacific Plate here moves fast enough that geologists consider it one of the most active subduction zones on the planet. The material being fed into the trench has been traveling across the Pacific Basin for tens of millions of years, cooling and thickening as it goes, and by the time it arrives at the trench, it is dense and cold and ready to descend. It does not hesitate at the edge. It simply goes under, pulled by its own weight into the mantle below. Earthquakes generated by the Tonga subduction zone number in the thousands every year. The zone produces more seismic events than almost any comparable region on Earth, and many of them occur deep, not at the surface of the plate boundary, but far down inside the descending slab, at depths where most rock would no longer fracture, but instead flow. Geologists call these deep focus earthquakes, and the Tonga region generates them regularly at depths of 600 kilometers or more. 600 kilometers below the seafloor, which is itself nearly 11 kilometers below the ocean surface. The forces involved are quiet from the outside. The ocean surface shows almost nothing, but the interior of the Earth at those depths is under pressures that compress the very minerals of the rock into new crystalline forms. Water at the bottom of the Tonga Trench is under a pressure of roughly 1,080 times the pressure at sea level. A simple way to feel that number. The air pressing down on your body right now exerts about 1 kilogram of force per square centimeter of skin. At the bottom of the trench, that becomes 1,080 kilograms on every square centimeter. Everything is being pressed from every direction simultaneously, not violently, but absolutely. A stillness enforced by weight. Water itself does not compress easily, but under these conditions, it does compress slightly, enough that the water at the very bottom of the trench is measurably denser than the water above it. The trench keeps its deepest layer a little more tightly packed than anything you would find at the surface. The temperature at the bottom of the Tonga Trench stays close to 1.5 degrees Celsius. This is not freezing. The water remains liquid, but it is barely above the point where fresh water would solidify. The near-freezing temperature exists because the deep water of the Pacific Basin is formed far away, near Antarctica, where surface water chilled by polar air becomes dense enough to sink and spread slowly across the ocean floor. That water left the surface perhaps 500 to 1,000 years ago. It has been traveling in the dark at near-freezing temperatures for centuries, arriving at the trench floor as a slow and ancient current that has not seen light since before any living person was born. Light disappears from the ocean at roughly 200 meters depth, and the Tonga Trench descends more than 50 times deeper than that. Below the sunlit zone, there is a faint twilight layer, and below that, there is nothing. Pure darkness, unbroken for 10.5 kilometers of water column. The darkness is not like the darkness of a room with the lights off. There is no surface to reflect anything, no ambient glow from any direction. It is the kind of darkness that existed before eyes evolved to need it otherwise. Whatever lives down there does not experience blindness as a loss. This has simply always been the condition of the world. Life exists at the bottom of the Tonga Trench. The first explorers to sample sediment from the deepest portions of the trench found it populated. Not densely, not abundantly, but with organisms that had adapted so completely to pressure and darkness and cold that they could not survive anywhere else. Among them are amphipods, small crustaceans shaped roughly like shrimp, which gather in the trench in numbers that surprise the scientists who found them. They feed on the slow drift of organic material that falls from the sunlit ocean far above. What researchers call marine snow, the constant, quiet precipitation of dead cells and particles that descends for days before reaching the floor. The amphipods wait for it. They have been waiting for it, in one form or another, for a very long time. Marine snow takes roughly 16 days to travel from the sunlit surface to the floor of the Tonga Trench, a particle leaving the surface. A fragment of a dead organism, a fecal pellet, a clump of algae, drifts downward through 10 kilometers of open water, slowing as it sinks, spinning slightly in currents that grow calmer the deeper it goes. By the time it reaches the floor, it has passed through every zone of the ocean. The sunlit layer, the twilight zone, the midnight zone, the abyssal zone, and finally the hadal zone, which begins at 6,000 meters and contains the trench floors of the world. Each zone is colder and darker than the one above it. The particle arrives changed. Bacteria have been working on it the entire way down. The hadal zone, the name given to the deepest portions of ocean trenches, covers less than 1% of the total ocean floor by area, yet it contains conditions found nowhere else on the planet. The word hadal comes from Hades, the ancient Greek name for the underworld, though the scientists who coined the term seem to have meant it geographically rather than dramatically. Trenches like the Tonga represent isolated pockets of extreme depth, separated from each other by vast stretches of shallower seafloor, which means the species that evolve inside them often cannot reach other trenches. Each trench becomes its own world, its own long experiment in what life becomes when the conditions are unlike anything above. The Tonga Trench sits atop one of the most geologically young pieces of seafloor in the Pacific. The ocean crust at the surface of the subducting plate in this region is between 90 and 100 million years old. Ancient by human measure, but young for oceanic crust, which can reach ages of around 200 million years in other parts of the world. As crust ages, it cools and thickens and becomes denser. And denser crust sinks more readily when it meets a subduction zone. The relatively young plate here still sinks, but at the extraordinary speed that makes the Tonga Trench so seismically busy. Older, heavier crust pulls itself down. Younger crust is pulled down by the geometry of the zone it is entering. Volcanoes form behind the Tonga Trench on the side, away from the subducting plate. As the Pacific Plate descends, it carries with it water locked inside hydrated minerals. Water that was incorporated into the rock, perhaps hundreds of millions of years ago at a mid-ocean ridge far away. When that rock descends far enough and heats enough, the water is released into the overlying mantle. Water lowers the melting point of rock, and so the mantle above the descending slab begins to melt. That melt rises slowly over thousands of years, and where it reaches the surface, it forms volcanoes. The Tonga Arc, a curved chain of islands and submarine volcanoes running roughly parallel to the trench, is the visible expression of this process. Tofua is a volcanic island in the Tonga Arc with a caldera lake at its summit. The island rises from the ocean directly above the zone where the subducting Pacific Plate is generating melt in the mantle below. At the surface, Tofua looks like a quiet tropical island. Green slopes, still water in the crater, seabirds above. Beneath the surface, the same geological process that carved the trench to the east is feeding magma upward through the crust. The island and the trench are products of the same slow event, one pressing down and one pushing up, separated by the width of the arc, roughly 200 kilometers, give or take, and connected by nothing visible at the surface. The floor of the Tonga Trench has been visited by crude submersibles only a handful of times. The engineering challenge of building a vessel that can survive over 1,000 atmospheres of pressure while remaining controllable and recoverable is significant. And for most of the trench's known history, the only contact humans had with its floor was through unmanned probes and dredge samples pulled up on cables. The deepest portions were mapped in detail for the first time using multi-beam sonar, instruments that send pulses of sound downward and reconstruct the shape of the bottom from the returning echoes. The maps produced this way have a resolution of roughly 25 meters, meaning features smaller than a generous living room remain invisible. Sound travels through water faster than through air. About 1,480 meters per second at the surface, compared to 343 meters per second in air. In the deep ocean, the speed of sound changes with temperature, pressure, and salinity, and the result is a natural acoustic layer called the SOFAR channel, an abbreviation that stands for sound fixing and ranging, where sound becomes trapped and can travel extraordinary distances without losing much energy. Whales use this channel to communicate across ocean basins. In the deep water approaching the Tonga Trench, the SOFAR channel exists above the trench itself. The trench plunges below it into a region where the acoustics behave differently and sounds decay faster. The deepest fish ever recorded was filmed inside the snailfish family, a pale, translucent creature observed at around 80,300 meters depth in the Izu-Ogasawara Trench, not far from Tonga in geological terms. Snailfish of related species have been recorded in the Tonga Trench as well, and they represent the boundary of what vertebrate life can endure under pressure. Beyond a certain depth, the pressure disrupts the molecular machinery inside cells. particularly the proteins that allow enzymes to function. Snailfish have evolved a biochemical stabilizer called trimethylamine oxide, or TMAO, which counteracts this disruption. The deeper the fish, the higher the concentration of TMAO in its tissues, a natural antifreeze for the laws of physics. The sediment on the floor of the Tonga Trench is different from the sediment found on the abyssal plains surrounding it. On the open ocean floor, sediment is dominated by the shells of tiny organisms, foraminifera and other calcifying plankton, that drift down from the surface and accumulate slowly over millions of years. But below a depth of about 4,000 meters, seawater becomes corrosive enough to dissolve calcium carbonate, and the shells disappear. In the deepest parts of the trench, the sediment is instead made mostly of clay and silica, the leftover fraction that survives the long dissolving descent. It is some of the slowest accumulating sediment on Earth. A layer just a few centimeters thick may represent millions of years of deposition. Hydrostatic pressure in the trench increases by roughly 1 atmosphere for every 10 meters of depth. At 10,800 meters, the pressure is approximately 1,080 atmospheres, which means a sealed airspace at that depth would be compressed to less than 1/1000th of its original volume. A balloon inflated at the surface and carried to the trench floor without bursting would shrink to the size of a grape. The volume reduction is direct and mechanical. The water pressing in from every side is simply stronger than the air pressing out. This is why submersibles designed for full ocean depth must have pressure hulls of extraordinary thickness. Some made from titanium spheres with walls nearly 9 centimeters thick to contain a small breathable space inside. The Tonga Trench is part of a broader system called the Tonga Trench, which extends southward toward New Zealand and represents one of the longest continuous trench systems on the planet, stretching for roughly 2,500 kilometers. The northern section, closer to the Tonga Islands, contains the greatest depths. As you move south, the trench gradually becomes shallower and the character of the subducting plate changes. The full system forms a continuous geological feature, but scientists often treat the two sections separately because the processes operating in each differ in measurable ways. Different speeds, different depths, different patterns of seismicity. The Tonga Islands themselves are built partly from material that has been scraped off the subducting Pacific plate as it descends. This process, called accretion, piles sediment and volcanic rock into wedges at the leading edge of the overriding plate. Over millions of years, this material consolidates and rises. Some of what you would stand on if you visited the Tonga archipelago was once seafloor moving toward the trench from the east. Material that arrived at the subduction zone and, rather than descending, was added to the edge of the plate above. It is now island. The Tonga Trench produces something the surface world rarely notices: very low frequency sound. When the plates shift against each other in small adjustments too subtle to be felt as earthquakes, they generate acoustic energy that propagates through the water. Hydrophones, underwater microphones, placed in the Pacific, have recorded this background sound for decades, and researchers have learned to read it the way a physician reads a heartbeat: rhythms and irregularities that tell the story of what the earth below is doing. The trench is not silent. It hums, very quietly, in frequencies below what the human ear can detect. A sound older than any instrument built to hear it. The trench pulls heat out of the Pacific floor as it swallows the plate beneath. When oceanic crust descends into the mantle, it carries cold temperature with it. Crust that has spent millions of years far from any volcanic heat source and is far cooler than the surrounding rock. That temperature difference matters. The descending slab chills the mantle around it, and geophysicists can detect that cooler region using seismic waves, which slow slightly as they pass through it. The cold ghost of the Pacific Plate can be traced hundreds of kilometers below the trench floor, a thermal shadow pressing steadily downward into the planet's interior. In this way, the trench is not only a hole in the ocean floor, but a duct carrying the cold of the deep sea into the deep earth. The Tonga Arc produces some of the fastest ground movement rates ever measured. The islands and submarine ridges that sit above the subduction zone are being pulled apart and squeezed at the same time, stretched by the rollback of the descending plate and compressed by the collision itself. GPS stations placed on the Tongan Islands have recorded horizontal movement rates of up to 15 centimeters per year. That's roughly the length of a human hand, shifted in a single year. Averaged across the arc, the crust here moves faster than almost any other comparable structure on the planet. The ground beneath the islands is in slow, continuous motion, though it remains perfectly still beneath anyone standing on it on any given morning. Seawater enters the trench and does not simply collect there. It is drawn inward through cracks and faults in the descending plate, carried many kilometers below the ocean floor in a process called subduction hydration. Water molecules bond chemically with minerals in the crust, becoming locked into the rock structure rather than remaining as free liquid. In this form, water can survive pressures and temperatures that would boil it instantly if it were free. It travels with the plate for millions of years, releasing only when the plate descends deep enough for the pressure and temperature to break the chemical bonds, at which point it escapes upward and triggers the melting that feeds the volcanoes above. The water that enters the trench does not return to the ocean the way it left. Hot water vents have been found along the Tonga Arc at depths of nearly 2 kilometers. Hydrothermal vents form where seawater penetrates fissures in the seafloor, is superheated by the magma below, and rises back through the crust carrying dissolved minerals. Along the Tonga region, the venting is especially active because volcanic heat is close to the surface and the faulting is extensive. The water that emerges from these vents can exceed 300 degrees Celsius, well above the boiling point at sea level. But at that depth, the pressure keeps it liquid. Around each vent, the minerals it carries precipitate out as the water cools, building towering chimneys of sulfide and oxide minerals that can reach the height of a 4-story building over decades. The seafloor along the Tonga Arc contains mineral deposits that took millions of years to accumulate. Hydrothermal venting over geological timescales builds up concentrations of metals: copper, zinc, gold, and silver, embedded in the mineral structures around vent fields. These deposits form because the superheated water leaches metals from deep rock and deposits them when it cools at the seafloor. In the Tonga region, researchers have mapped several of these fields, each one a record of past volcanic and tectonic activity frozen into the seafloor itself. Every layer in those deposits corresponds to a period of heat, pressure, and fluid flow that occurred long before any human eye had seen the bottom of this ocean. The deepest fish ever recorded was found in a trench in this same region of the Pacific. A snailfish, a pale, translucent creature with no hard skeleton, was captured on camera at a depth exceeding 8,000 meters, drifting slowly through water that was barely above freezing. Snailfish of this kind have evolved bodies that work precisely because of the pressure around them, not despite it. Their cell membranes and proteins are tuned to function only under conditions that would disable the same structures in a surface fish. They are, in the most literal sense, built for this. Brought to the surface, they would not survive, because the world they are adapted to exists only at the bottom of places like this. Submarine landslides along trench walls can be among the largest mass movements on Earth. The walls of the Tonga Trench descend at angles steep enough that material periodically breaks free and slides downward. Sediment, fractured rock, and the remnants of seamounts that have been partially consumed by the subduction process. Some of these underwater slides displace volumes of material comparable to entire mountain ranges. They happen slowly by human timescales, sometimes triggered by earthquakes, and they leave behind chaotic debris fields that spread across the trench floor. A geological survey of the trench walls reads like a catalog of ancient collapses, each one silent and invisible to the surface world above. The spreading center behind the Tonga Trench is one of the fastest on the planet. As the Pacific Plate pulls away and sinks, the overlying crust stretches and in some places splits apart, creating a back arc basin. A region of seafloor spreading that mirrors, in a smaller way, the spreading centers at mid-ocean ridges. The Lau Basin, which sits just behind the Tonga Arc, is opening at a rate of up to 160 mm per year in some sections. That's roughly the width of a human palm every 12 months. New seafloor is being created here even as old seafloor disappears into the trench a few hundred kilometers away. The basin is both forming and widening in the same geological instant. Manganese crusts grow on the walls of the trench at a rate almost too slow to name. In parts of the deep ocean where hydrothermal activity is absent, manganese and iron slowly precipitate out of seawater and coat-exposed rock surfaces in thin, dark layers. The growth rate is roughly 1 to 2 millimeters per million years, meaning a crust 1 centimeter thick represents somewhere between 5 and 10 million years of uninterrupted deposition. Along the walls of the Tonga Trench, these crusts coat rock faces that have been exposed since the trench itself reached its current depth. They are among the slowest growing structures in the natural world, built grain by grain from the seawater moving past them in the dark. The shape of the trench affects how tsunamis move across the Pacific. When a large earthquake occurs along the Tonga subduction zone, it displaces an enormous column of water above it, and that displacement travels outward as a wave in all directions. The geometry of the trench, long and narrow, oriented roughly north to south, influences how that wave energy is focused. Waves traveling perpendicular to the trench axis carry more energy than those traveling along it, a pattern that oceanographers can use to anticipate which coastlines receive the most energy from a given event. The trench, in this way, is not just a geological structure. It is a shape that the ocean remembers when it moves. Colonies of foraminifera live even at the greatest depths of the trench system. Foraminifera are single-celled organisms that build intricate shells of calcium carbonate, and they have existed in the oceans for hundreds of millions of years. In the shallower portions of the trench, they are abundant, but as depth increases, pressure dissolves calcium carbonate faster than it can accumulate, and their shells disappear from the sediment record below a boundary called the carbonate compensation depth. Below that line, the trench floor holds no calcareous remains at all, only bare clay and the silica skeletons of organisms that can survive the dissolution. The transition from shell-bearing sediment to bare red clay marks a chemical boundary as clear as a line drawn in the water. Bioluminescent organisms drift through the mid-water column above the trench in enormous numbers, at depths between 200 and 1,000 meters. The twilight and midnight zones. An estimated 76% of all marine organisms are capable of producing light, They flash and glow in patterns specific to their species, using light to attract prey, deter predators, or communicate with potential mates in a world where sunlight has never reached. Above the Tonga Trench, where the water column is exceptionally deep, this living light show extends through a vertical stretch of ocean that in some places exceeds 9 kilometers from surface to floor. If you could see the full water column in darkness, it would appear less like an empty void and more like a dim, pulsing galaxy moving in slow currents. The crust beneath the trench has been folded by its own descent. As the Pacific plate bends downward at the trench, it does not fold cleanly. The outer rise, just seaward of the trench, bulges slightly upward as the plate flexes, and the crust there is stretched and faulted by the bending stress. These faults allow seawater to penetrate deeply into the crust even before it reaches the trench itself, pre-hydrating the plate before subduction begins. By the time that same crust arrives at the trench axis and begins its descent, it has already absorbed water through hundreds of kilometers of prior bending. The trench, in this sense, begins its work before the plate ever reaches it. Sound generated at the surface can, under the right conditions, reach the floor of the trench. The deep sound channel, the SOFAR channel, guides low-frequency sound through the ocean at the depth where sound speed reaches its minimum, typically between 600 and 900 meters. Sounds entering this channel can travel thousands of kilometers with almost no energy loss. Below the channel, sound refracts back upward. Above it, sound refracts downward. At very low frequencies, however, sound energy that enters the water column can scatter throughout the full depth, reaching the trench floor as a faint and diffuse rumble. The deep ocean is not silent. It carries a permanent, low background noise composed of distant storms, ships, and the creaking of the earth itself. The Tonga region hosts some of the most isolated island communities in the Pacific. The islands of Tonga sit atop the arc produced by the subduction zone, and the people who have lived there for more than 3,000 years built ocean-going cultures precisely because isolation demanded it. Navigation across these waters required reading stars, wave patterns, and the behavior of seabirds. A form of environmental literacy that encoded knowledge about the ocean in ways that had nothing to do with instruments. The trench itself was unknown to them in its full depth, but the earthquakes and eruptions it produces were not. They were woven into oral traditions as explanations for a world that shook and burned and rose from the sea. Whale song can be detected by hydrophones positioned near the Tonga Trench. Humpback whales migrate through the waters above the trench in their low-frequency calls, which can last for hours and carry for hundreds of kilometers. Pass through the same deep-water acoustic channels that carry other long-distance sounds. Researchers studying deep ocean acoustics have recorded whale vocalizations at monitoring stations positioned near the trench, along with the low rumble of distant earthquakes and the occasional sharp crack of tectonic faulting. The same water column that reaches from the surface down to the darkest part of the trench carries all of these sounds simultaneously, layered atop one another, traveling in different directions at slightly different speeds. The ocean above the trench has its own layered structure that mirrors the geology below. Oceanographers divide the water column into distinct zones defined by temperature, salinity, and light. The sunlit epipelagic, the dim mesopelagic, the lightless bathopelagic, each one a distinct habitat with its own communities of organisms. Above the Tonga Trench, these zones are especially deep because the trench adds several kilometers of hadal zone below what the rest of the ocean contains. The result is a water column with more distinct vertical layers than almost anywhere else on the planet, each layer populated by organisms that have never seen the one above or below it. The trench does not just reach down into the earth. It extends the ocean upward in layers all the way to the surface. Copper and manganese nodules litter the seafloor and regions surrounding the trench. These potato-sized concretions form when dissolved metals slowly precipitate around a small nucleus. A shark tooth, a fragment of shell, a grain of sediment, and accrete over millions of years. In some parts of the Pacific, nodule fields cover the seafloor in a dense carpet, each nodule representing between 1 and 10 million years of slow chemical growth. Around the edges of the Tonga system, where the seafloor has been stable long enough for accretion to proceed, these nodules can be found resting on the sediment surface exactly where they grew, undisturbed, in the dark and the cold, for longer than our species has been on Earth. The Tonga Trench has its own effect on the global circulation of deep water, the deepest water masses of the Pacific. Cold, dense, oxygen-rich water that sank at polar latitudes and has been traveling along the ocean floor for centuries, flows northward and is partly blocked or deflected by the geometry of the trench and the surrounding ridges. The trench sits within the path of this slow-moving abyssal current, and its walls and floor influence how that water moves, where it pools, and how long it remains at depth before eventually mixing upward into shallower water. The trench is not only a geological structure, it is a dam, a corridor, and a reservoir within the largest circulation system on the planet. The oldest rocks on the overriding plate above the trench are far younger than the plate descending into it. The Pacific Plate carries crust that is up to 170 million years old, formed at spreading centers long gone and traveled halfway around the planet since then. The crust on the other side of the trench, the plate being overridden, is geologically young. In some areas, only a few million years old, formed by the back arcs spreading that the subduction itself drives. These two pieces of crust meet at the trench axis, one ancient and cold and dense, one young and thin and buoyant. Their difference in age is one of the reasons the old plate sinks and the young one rides above it. Density, accumulated over 160 million years of cooling, pulls it steadily down. The trench floor is almost entirely dark, yet it is not entirely still. At the very bottom, slow-moving currents called benthic flows move along the floor like the breath of something vast and unhurried. They are driven not by wind or tide, but by tiny differences in water density. A fraction of a degree cooler, a fraction saltier. And those differences are enough to keep the water shifting very slowly for centuries. Scientists have traced some of these bottom currents back to their origin points thousands of kilometers away in the cold polar waters of the Southern Ocean. The trench floor receives them at the end of a journey that may have taken hundreds of years to complete. Even at the very bottom, the water is not resting. The sediment on the trench floor contains a record of every major volcanic eruption in the Western Pacific for the past several million years. When a volcano erupts violently enough, it sends a fine layer of ash drifting across the ocean surface. Over weeks and months, the ash settles slowly downward through the water column and eventually comes to rest on the seafloor. In the Tonga Trench, those ash layers are preserved in the sediment in the order they fell. One thin, pale stripe per eruption, stacked atop one another like the pages of a very old book. Geologists can core through them and read backward in time, matching each layer to a known eruption or discovering ones that left no record on land. The trench, in this way, is also an archive, patient, dark, and undisturbed. Seawater entering the trench carries dissolved oxygen that living things at the bottom actually use. This might seem surprising. The trench is sealed from the surface by 10 kilometers of water. But the cold, dense currents that flow along the trench floor carry oxygen that was absorbed from the atmosphere long ago, before those waters sank. It is old oxygen, in a sense, trapped in the water when it was last at the surface, perhaps centuries back. Yet it remains available to the creatures and microbes at the bottom, who depend on it just as any organism depends on the air around it. The deep trench is, in its way, still connected to the sky above, through water that remembers touching it. The walls of the Tonga Trench slope inward at an angle that changes depending on where you measure. Along some stretches, the walls descend at a relatively gentle pitch, carved gradually by the slow creep of sediment and the bending of the plate beneath. In other places, especially near seamounts that have been dragged into the subduction zone, the walls are nearly sheer, dropping steeply for several kilometers with almost no ledge to interrupt them. This variation is not random. Each change in angle records a different episode in the trench's history: a period of faster plate movement, an unusually large seamount that was subducted, a fault that opened the wall outward. The trench's geometry is a sentence written in the language of deep time. Earthquakes in the Tonga subduction zone happen at depths that almost no other zone on Earth can match. Most subduction zones generate earthquakes down to about 300 kilometers below the surface. In the Tonga region, earthquakes have been recorded at depths exceeding 600 kilometers. That's 600 kilometers, roughly the distance between two large cities in the same country, making them among the deepest seismic events ever measured. At these depths, the rock is under such extreme pressure that it no longer fractures in the usual sense. Instead, it undergoes a kind of sudden phase change, a transformation in its crystal structure that releases energy in the same way a more ordinary earthquake would. These events are called deep focus earthquakes, and the Tonga zone produces more of them than almost anywhere else. The overriding plate above the Tonga subduction zone is not one solid piece. Rather than a single continuous slab, the plate on the western side of the trench is broken by a series of rifts and spreading centers that pull it apart even as the Pacific plate pushes beneath it. This creates a dynamic that geologists find unusually complex. One part of the system is consuming crust, while another part, just a few hundred kilometers away, is creating new crust from below. The Lau Basin, which spreads open behind the Tonga Arc, is one of the places where new seafloor is actively being born, thin, fresh, and warm, while the old Pacific crust ahead of it is being swallowed. Creation and consumption, running side by side. The temperature at the very bottom of the Tonga Trench is close to just above freezing. Near the trench floor, the water temperature hovers somewhere between 1 and 2 degrees Celsius. That's cold enough that you could keep perishable food fresh in it indefinitely, without any refrigeration at all. This extreme cold is not left over from some ancient ice age. It is continuously refreshed by the slow conveyor of deep ocean circulation, which brings cold polar water down and along the seafloor, replacing what is already there. The creatures that live at these depths have spent millions of years adapting to a world that never warms, never brightens, and never changes its temperature by more than a fraction of a degree across a whole year. Some of the water in the Tonga Trench is older than any living thing on Earth's surface. The deep water circulating near the trench floor may have last seen the sky during a period of human history that we would consider ancient. Some estimates place the age of certain deep Pacific water masses at over 1,000 years. During that time, it has drifted through the dark, carried slowly by density currents, absorbing nothing from the surface world. It does not know about the civilizations that rose and fell while it traveled. It carries only the chemistry of the ocean, its dissolved minerals, its ancient oxygen, its patient salts. When it finally rises back to the surface, centuries from now, it will meet a world entirely different from the one it left. Pressure in the Tonga Trench compresses not just solid objects, but the water itself. At the greatest depths, seawater is measurably denser than it is at the surface, squeezed together by the weight of everything above it. In practical terms, a column of water at trench depth is roughly 5% more dense than the same water at the surface. That may sound like a small difference, but across the vast volume of the trench, it represents an enormous amount of energy stored in compression. When scientists bring up water samples from these depths in sealed containers, the containers must be carefully managed. The pressure difference between inside and outside, once the sample reaches the surface, can be enough to rupture improperly designed equipment. The deep ocean pushes back against everything that tries to contain it. The Tonga Arc has produced some of the largest underwater volcanic explosions in recorded history. The 2022 eruption of Hunga Tonga Hunga Hunga Ha'apai, which occurred along the Tonga volcanic arc, sent a pressure wave around the Earth multiple times. Not once, not twice, but several times, measured by weather stations as far away as the opposite side of the planet. The eruption column reached into the mesosphere, roughly 57 kilometers high. That is more than 5 times the cruising altitude of a commercial aircraft. The explosion was heard thousands of kilometers away, and yet it rose from an undersea volcano that had been building quietly for years, mostly hidden beneath the surface. The arc that produced it runs the full length of the Tonga region, fed by the same subduction that shapes the trench beneath. The trench acts as a kind of gravitational low point for the surrounding seafloor. Because the Pacific plate is being pulled downward into the mantle, it creates a slight depression in the surrounding region, a subtle warping of the seafloor that extends outward from the trench for hundreds of kilometers. This outer trough is not as dramatic as the trench itself, but it is measurable, and it affects how sediment moves across the abyssal plain. Material that might otherwise drift freely across the deep seafloor is instead slowly guided toward the trench, funneled by the gentle tilt of the plate. Over millions of years, this has made the Tonga Trench a collector, accumulating not just sediment, but a record of nearly everything that has passed through the water above it. The rate at which the Tonga subduction zone consumes seafloor is among the highest on Earth. Each year, roughly 24 centimeters of Pacific plate disappears beneath the overriding plate. 24 centimeters, about the width of a standard dinner plate, erased from the surface of the Earth and pulled into the mantle. Over 1 million years, that adds up to 240 kilometers of crust consumed. Over the full lifespan of this subduction zone, hundreds of thousands of kilometers of seafloor have vanished into the deep interior of the planet. The trench is not just a feature of the landscape. It is an engine of geological destruction on a scale that the human mind can barely hold. Amphibious microbes near the trench can survive both crushing pressure and near-zero temperatures simultaneously. Scientists studying sediment cores from the trench floor have found microbial communities that are not merely tolerant of the conditions, but appear specifically adapted to them. These organisms, most of them single-celled, have evolved proteins and membrane structures that remain flexible and functional at pressures that would denature almost any molecule built for surface conditions. Their chemistry is, in a sense, written for a different world, one where the rules of pressure and temperature are inverted from what most life on Earth experiences. They may represent some of the oldest lineages of life on the planet, cousins to organisms that thrived in Earth's early oceans before the surface became hospitable. The Tonga Trench has a measurable gravitational signature detectable from orbit. Satellites equipped with radar altimeters can detect the very slight dip in the ocean surface caused by the reduced mass below the trench. Because there is less rock beneath the trench than beneath the ordinary seafloor, the ocean surface above it dips by a few meters. That dimple is invisible to the eye but real, and it allowed scientists to map the approximate shape of the world's oceanic trenches before any submersible had ever reached their floors. The Tonga Trench was sketched from space before it was visited from the deep. Gravity, patient and all-encompassing, gave it away. Abyssal amphipods living in the Tonga Trench carry chemical traces of the surface world in their tissues. These small crustaceans, sometimes reaching 8 centimeters in length, roughly the length of your index finger from knuckle to tip, feed on organic material that drifts down from far above. When scientists have analyzed their tissues, they have found compounds that originated in surface plankton, in the remains of fish that lived in the sunlit zone, and in other organisms that never descended anywhere near the trench. The amphipods are, in this way, a living link between the surface ocean and the deep, carrying the chemistry of sunlight into a world that has never seen it. The Tonga Trench sits at the intersection of two entirely different tectonic worlds. To the east lies the ancient Pacific Plate, cold, dense, and old, its crust having formed during the age of the dinosaurs. To the west lies a patchwork of younger, thinner plates. The Tonga Plate, fragments of the Australian Plate, newer and still being shaped by volcanic activity above and below. The trench is the line where these two worlds press against each other, and neither gives way willingly. The energy of that contact is released in earthquakes, channeled into volcanic eruptions, and stored in the slow deformation of both plates over millions of years. It is one of the most tectonically active meeting points on the planet. Deep-sea currents flowing along the Tonga Trench floor carry nutrients that eventually reach the surface ocean. The slow upwelling that occurs along the trench margins, driven by density differences and the gentle stirring of tidal forces, brings nutrient-rich deep water gradually upward over time. This process, called deep mixing, takes centuries, but its effects are real. The nutrients that once settled to the bottom as organic debris eventually return to the sunlit zone, where they feed phytoplankton, which feed the entire food web above. The trench does not simply receive material from above. It also gives back, slowly, in a cycle that has been running for as long as the trench has existed. Sound produced by earthquakes in the Tonga subduction zone can be detected on the far side of the Pacific Ocean, the deep sound channel of the ocean. A layer of water where sound travels with unusual efficiency, sometimes called the SOFAR channel, acts like a waveguide, preserving low-frequency energy across enormous distances. Seismic events near Tonga have been recorded by hydrophones positioned off the coasts of North America and beyond. The sound travels not through the air, but through the water, at a speed of roughly 1.5 kilometers per second, covering the breadth of the Pacific in just over 2 hours. The trench speaks, and the whole ocean listens. The deepest parts of the Tonga Trench have almost certainly never been fully mapped at high resolution. Even with modern multi-beam sonar systems, the narrowest and deepest sections of the trench remain surveyed only at coarse resolution. The width of the trench floor in its deepest sections can be less than a kilometer, and the angle of the walls makes precise acoustic mapping difficult. Some sections of the floor may contain features, ridges, depressions, low volcanic cones that have never been clearly imaged. There are places in the Tonga Trench that are, in a very practical sense, still unknown. The map is not finished. It may not be finished for a very long time. The weight of the water column above the Tonga Trench floor is equivalent to placing a mass of roughly 1,000 kilograms on every square centimeter of the bottom. 1,000 kilograms per square centimeter. That is the weight of a small car balanced on a surface no larger than your thumbnail. Every centimeter of the trench floor bears that load continuously, without interruption, and yet the floor does not collapse. The rock beneath it, compressed, ancient, and cold, holds. The sediment rests. The microbes go about their slow business. The trench endures its own weight the way a sleeping body endures gravity. Simply, without resistance, as if it had never known any other way to be. The trench floor is almost perfectly dark, yet it is never truly still. Water moves there, slowly, continuously, invisibly. Cold density currents edge along the bottom like a breath drawn in over thousands of kilometers, carrying oxygen that entered the ocean near the poles and traveled for centuries before arriving at this depth. The movement is so gradual that it cannot be measured by watching, only by sampling water chemistry at different points and calculating what must have happened between them. No light reaches the floor to mark the passage of time. The movement is felt only in the chemistry, in the slow renewal of oxygen that keeps even the deepest sediment alive with microbial activity. The sediment at the trench floor holds a record of every eruption in the surrounding region for tens of millions of years. Thin layers of volcanic ash settle through the water column after each eruption, eventually coming to rest on the floor in precise sequence. Oldest at the bottom, youngest near the surface. Geologists reading these layers can reconstruct the eruptive history of the Tonga Arc the way a reader turns pages, one event at a time. Some ash layers are so thin they are measured in millimeters. Others, from larger eruptions, are thick enough to be visible without magnification. Each layer represents a moment when the sky above the Pacific was briefly altered, and the trench floor quietly caught the evidence. The deepest water in the Tonga Trench is slightly saltier than the water above it. This is not because salt accumulates there. It is because pressure itself compresses seawater, making a given volume fractionally denser and concentrating its dissolved content. The effect is small, but measurable. A liter of seawater drawn from near the trench floor weighs a little more than a liter drawn from the surface. Not because its composition has changed, but because pressure has squeezed it into less space. The ocean at depth is a denser version of itself, the same water made more compact by the weight of everything above. The walls of the trench are not uniform. They record thousands of years of slipping, settling, and reshaping. Where the Pacific plate bends downward into the subduction zone, the crust fractures along its outer edge, creating a series of fault lines parallel to the trench itself. These outer rise faults are among the quieter features of the system. They do not produce the largest earthquakes, but they do something else. They let seawater in. Water seeps into the cracks before the plate descends, traveling down with the crust and eventually reaching depths where pressure and temperature transform it into something the mantle can absorb. The walls of the trench, in this way, are not just a boundary. They are a slow entry point for the surface world. Sediment on the trench floor travels inward from the surrounding seafloor over long timescales. The trench sits slightly lower than the abyssal plain around it, low enough that fine particles drift toward it the way dust drifts toward the corner of a room. Over millions of years, this funneling effect has concentrated material in the trench that originated far away. Some of the sediment on the floor contains minerals and biological material from regions of the Pacific that are hundreds of kilometers distant. The trench does not only receive what falls directly above it, it gathers slowly and patiently from a much wider neighborhood. The snailfish found in the deepest parts of the trench has no swim bladder. Most fish use a gas-filled bladder to regulate their buoyancy. But at pressures exceeding 1,000 atmospheres, gas-filled chambers would collapse instantly. The snailfish instead relies on a body that is soft, semi-transparent, and largely composed of water, a form so adapted to pressure that it could not survive near the surface. Brought upward quickly, it would not simply die. It would disintegrate, its tissues unable to hold together in the reduced pressure of shallower water. It is an animal shaped entirely by the place it lives, as perfectly fitted to the deep as a hand inside a glove. The trench generates a particular kind of silence, one that is not the absence of sound, but the absence of light. Sound, as noted earlier, travels efficiently at depth, channeled by pressure and temperature into long ribbons of detectable energy. But light behaves differently. Even the faintest trace of sunlight is fully absorbed within the first 200 meters of the water column. Everything below that threshold exists in permanent darkness. The trench floor, lying more than 10 kilometers beneath the surface, has never once been touched by sunlight in any form. The darkness there is not like a room with the lights off. It is absolute, unbroken, and has persisted for as long as the trench has existed. Water that enters the trench through outer rise faults may eventually return to the surface, but not for millions of years. Once subducted with the descending plate, water locked into the crystal structure of minerals is carried to depths where temperature and pressure eventually break those mineral bonds and release it again. Some of that water rises slowly through the overlying mantle and contributes to the partial melting that feeds the Tonga Arc volcanoes. The eruption of a Tongan volcano is, in part, the return of water that entered the ocean floor perhaps 30 or 40 million years earlier. Surface water completing a journey too long to be measured in any human term. The trench has a measurable gravitational signature that extends all the way to space. Because the trench represents a region where dense oceanic crust is being pulled downward and replaced by water, the local distribution of mass in that part of the Earth is unusual. Satellites in orbit can detect the subtle variation in gravitational pull as they pass overhead. The ocean surface above the trench actually sits slightly lower than it would otherwise, pulled inward by the mass anomaly below. This creates a gentle depression in the sea surface, measurable from orbit, that corresponds almost exactly to the location of the trench beneath. The shape of the water maps the shape of the rock below it. The Tonga Arc has produced eruptions that sent material all the way into the stratosphere. When large submarine or shallow water eruptions occur along the arc, the interaction between seawater and magma can generate columns of gas and debris that rise far higher than a typical land-based eruption. The 2022 Hunga Ha eruption reached the mesosphere, the layer of the atmosphere that begins roughly 80 kilometers above the Earth's surface. The pressure wave it generated was measurable on instruments worldwide, not once but multiple times, as it circled the Earth and bounced back from the far side. An eruption at the edge of the trench sent a ripple through the atmosphere of the entire planet. The microbes living in the trench sediment belong to lineages that diverged from surface life hundreds of millions of years ago. In the deep sediment, organisms have been adapting to conditions of near-freezing temperature, crushing pressure, and near-total darkness for so long that their cellular machinery has been substantially rebuilt. Their proteins fold differently, engineered by evolution to remain stable under pressures that would denature the proteins of a surface organism instantly. They do not merely tolerate the deep, they require it. Some of these lineages likely have no close relatives anywhere in the sunlit ocean. The trench floor is, in a genetic sense, its own world. The Tonga Trench lies within one of the most seismically productive regions on Earth. The subduction zone produces earthquakes at nearly every depth. Shallow, intermediate, and deep focus. Because the descending Pacific plate remains rigid enough to fracture even hundreds of kilometers below the surface. On average, the region generates more magnitude 6 or greater earthquakes per year than almost anywhere else on the planet. Most of these are not felt at the surface with great intensity because they occur at depth. But the cumulative energy released over a century of Tongan seismicity would be staggering. An almost continuous slow-motion release of the energy stored in the bending and breaking plate. Manganese slowly coats the walls and edges of the trench in a layer no thicker than a coat of paint. This mineral crust grows at roughly 1 to 2 millimeters per million years. One of the slowest growth rates of any material in the natural world. The manganese is drawn from the surrounding seawater by electrochemical processes, grain by grain, across timescales that dwarf the existence of our species. A crust that is 1 centimeter thick has been accumulating since before the first hominids walked upright. The walls of the trench are, in this sense, not bare rock. They are slowly being painted in geological time. The trench floor receives organic material from the surface ocean, carried down through a process called the biological pump. When organisms in the sunlit surface waters die, their bodies begin to sink. Most are consumed in the upper water column, but a fraction. Small by proportion, enormous by total volume. Reaches the seafloor. Particles of carbon, once fixed by photosynthesis in the light-filled upper ocean, eventually come to rest in the darkness of the trench. There, they become food for the microbial communities that live in the sediment. The trench floor, utterly removed from sunlight, is nonetheless fed by it. Indirectly, slowly, through the long fall of once living things. The temperature at the bottom of the trench is just above freezing, and it has been that way for a very long time. Bottom water in the deep Pacific originates near the poles, where surface water chilled by cold air becomes dense enough to sink. It travels along the ocean floor for centuries before reaching the trench. The temperature it carries, typically between 1 and 2 degrees Celsius, is a record of polar conditions from centuries past. The cold at the trench floor is not local weather. It is a memory of a distant polar winter, preserved in water that has been traveling ever since. The back arc basin behind the Tonga Arc is spreading, pulling apart at one of the fastest rates measured anywhere on the ocean floor. The Lau Basin, which lies to the west of the Tonga Arc, is being stretched as the arc moves eastward above the subducting Pacific plate. New seafloor is being created there at rates that, in geological terms, are rapid, making the Lau Basin one of the most dynamic young ocean basins on Earth. What is happening in the Lau Basin is, in miniature, a version of what happened to the Atlantic Ocean hundreds of millions of years ago. A basin beginning its long expansion, floored by rock, that will eventually become ancient crust itself. The outer trench slope carries a series of faults that look, from above, like long parallel scars. These are outer rise faults, created as the Pacific Plate bends downward into the subduction zone and its outer surface stretches under the tension. Each fault is a crack in the crust, running roughly parallel to the trench axis, opened by the geometry of bending. Seen together, they give the outer slope a faintly ribbed appearance, like the surface of something flexed under great strain. The plate is not simply sliding beneath the overriding crust. It is bending, slowly and continuously, and those bends are recorded on its surface before it disappears beneath. The amphipods that colonize the trench floor carry chemical traces of surface life deep into the earth. These small crustaceans, some reaching lengths of a few centimeters, feed on organic material that sinks from the sunlit ocean above. Their tissues contain carbon compounds that can only have originated in photosynthesis, in the conversion of sunlight into organic matter by surface phytoplankton. When researchers have analyzed amphipod tissue from the deepest trenches, they have found compounds that link directly to the surface food web. The amphipod is a living bridge. Its body, a record of the sunlit world, even as it lives in perpetual darkness. The water above the trench is itself layered, each layer a different age, temperature, and origin. Near the surface, water is warmed by the sun and mixed by wind. Below the thermocline, it grows colder and older. Deeper still, it becomes a record of past centuries, carrying dissolved oxygen and carbon from the time it last touched the atmosphere. By the time you reach the trench floor, the water is ancient. It has not seen the sky since before many of the world's great cities were built. The trench does not sit at the bottom of a uniform ocean. It sits at the bottom of a stacked archive, each layer a different chapter of the same slow story. Everything that reaches the trench floor has traveled a long way to get there. The water above arrived from the poles centuries ago. The sediment drifted down from the sunlit surface, grain by grain. The organic carbon was once fixed by photosynthesis thousands of meters up. Even the cold is imported, carried in from distant polar regions by currents that have been moving since before written history. The trench floor is not a place apart from the rest of the ocean. It is the destination that everything eventually reaches, given enough time. The quiet endpoint of 1,000 slow journeys happening all at once. The trench sits inside one of the quietest regions of the deep Pacific. Above it, the open water stretches in every direction for thousands of kilometers. No continent is close. No shelf breaks the surface within reach. The Tonga Trench exists in a part of the ocean so remote that a ship traveling to it would spend days crossing water before seeing any change in the seafloor. That isolation gives the trench a quality that is hard to name. A kind of fundamental separateness from the rest of the world, as though it belongs to a different category of place entirely. It is not merely far away, it is a part. The crust descending into the trench has been cooling since the age of the first dinosaurs. When the Pacific Plate formed along mid-ocean ridges roughly 170 million years ago, it emerged as molten rock and began to cool immediately. Over tens of millions of years it contracted, hardened, and thickened as it drifted slowly westward. By the time it arrived at the Tonga subduction zone, it had become one of the oldest and coldest pieces of seafloor on the planet. Old crust is dense crust, and dense crust sinks more readily, which is part of why the Tonga Trench pulls its plate down so steeply and so fast. The plate's age is partly the engine of its own descent. The deepest water in the trench has not mixed with the open ocean in centuries. Far below the thermocline, far below the reach of currents and tides, and the slow churn of seasonal temperature change, the water in the trench's lowest regions becomes isolated. It arrives there through deep circulation and then effectively stops. Held in place by density and depth, refreshed only in the slowest geological sense. Scientists measuring the chemistry of trench bottom water find signatures consistent with water that has not seen the surface since before many modern nations existed. It is old water, sitting still, as patient as the rock that contains it. The walls of the trench are not smooth. They are fractured and terraced, carved by faults and slumps and the slow creep of sediment. In places, the wall drops nearly vertically for hundreds of meters before catching on a ledge. In other places, it steps down in broad shelves that collect the drifting remains of organisms from above. Submarine landslides have left scars wide enough that their upper edges are kilometers apart. The interior of the trench is, in this sense, a landscape. Complex, varied, and shaped by forces that have been operating continuously for tens of millions of years. It is not a whole, it is a country. The pressure at the trench floor exerts itself equally in every direction. This is the part that tends to be forgotten when imagining the deep. The pressure does not push downward. It pushes from all sides simultaneously, which is why creatures living there are not crushed the way a rigid container would be. Their bodies have no air pockets, no cavities where pressure could find purchase. The fluids inside them match the pressure outside them, and so they exist in a kind of equilibrium. The weight of 10 kilometers of ocean above is not felt as a weight. It is simply the condition of being there, as ordinary to the snailfish as sea level is to a sparrow. A slow rain of material has been falling toward the trench floor for millions of years. Marine snow. The fine, continuous drift of dead organisms, shed cells, and mineral particles sinks through the water column at roughly a centimeter per day. From the surface to the trench floor, that journey takes years. What arrives at the bottom is not fresh. It has been broken down, consumed, and reconstituted many times over on its way down. What finally reaches the sediment is a residue of a residue. Small, dark, rich in certain elements, and entirely unrecognizable from the living thing it once was. It feeds the microbes in the sediment below, completing a cycle that has been running since before any animal with eyes existed. Light has never touched the floor of the Tonga Trench. Not once in the 170 million years the Pacific Plate has been moving toward this zone. Not once in the tens of millions of years the trench itself has existed, has a photon of sunlight reached those depths. Sunlight penetrates to perhaps 200 meters in clear tropical water. The trench descends more than 10 kilometers. The gap between the last light and the floor is not a little darkness. It is an entire ocean's worth. Everything that has ever lived at the bottom of the Tonga Trench has done so without light, has metabolized without it, has reproduced without it, has died without it. The sediment at the trench floor carries a chemical memory of the surface ocean. Carbon and nitrogen isotopes in the organic matter that sinks from above reflect the conditions at the surface when those organisms were alive. The temperature of the water, the nutrients available, the biological activity of that particular period. By reading the sediment layers at depth, scientists can reconstruct something of the ocean's history. The trench acts as an archive, collecting and preserving these chemical signals in sequence, one thin layer at a time, going back through eras when the planet looked nothing like it does today. The floor remembers what the surface has long since forgotten. Water moves inside the subducting slab as a series of slow releases. As the plate bends downward and sinks into the mantle, the temperature and pressure around it increase. Minerals that locked water into their crystal structures when the seafloor was formed begin to break down at specific depths, releasing that water as fluid. The fluid does not travel quickly. It seeps upward through the overlying rock over thousands of years, eventually reaching the base of the overriding plate and triggering the partial melting that feeds the Tonga Arc volcanoes. Water that entered the seafloor as cold ocean was buried for millions of years, and now rises again as volcanic steam has completed one of the slowest journeys anything on Earth makes. The snailfish found near the trench floor have a body plan refined over enormous time. They are translucent and soft, without rigid bones in the places where rigid bones would trap pressure differentials. Their cell membranes contain unusual fatty molecules, piezolites, that keep the membranes flexible at pressures that would make ordinary lipids stiff and non-functional. Their proteins are folded in ways that resist the compressive forces of the deep. Each of these adaptations took millions of years to develop, selected for gradually as lineages of fish pushed deeper and deeper into environments that killed most of their ancestors. The fish alive in the trench today are the result of an enormous amount of invisible history. The Tonga subduction zone generates earthquakes at depths most subduction zones cannot reach. Earthquakes typically cease below about 300 kilometers, where the rock has become warm enough to deform plastically rather than fracture. But the Tonga slab is cold enough and descends fast enough to remain brittle to depths exceeding 600 kilometers, more than halfway to the Earth's lower mantle. Earthquakes at those depths are rare globally, and the mechanisms that produce them are still not fully understood. When one occurs, seismographs around the world record it as a signal arriving from a place that should, by most measures, be too deep and too hot to produce such a thing. The overriding plate above the trench is among the most tectonically complicated pieces of crust on Earth. It is not a single coherent slab, but a mosaic of small plates, rifts, and back arc basins, some spreading apart while others compress. The Lau Basin directly behind the Tonga Arc is splitting open at one of the fastest seafloor spreading rates measured anywhere on the planet, creating new ocean crust even as older crust is being consumed in the trench a few hundred kilometers away. Creation and destruction are happening simultaneously within the same regional system driven by the same subduction. It is a rare window into the full range of what plate tectonics produces. The trench exerts a measurable gravitational pull on the ocean surface directly above it. The missing mass of the trench. The absence of dense rock, where dense rock normally would be, creates a slight deficit in the gravitational field. The ocean surface, which everywhere tries to settle at an equal gravitational potential, dips very slightly above the trench. By roughly 40 meters over the span of the feature, this dip is imperceptible to any ship crossing it. The slope is far too gradual for any instrument on the surface to detect, but it is real, and it has been mapped by satellite altimeters, which trace the ocean surface with enough precision to read this gravitational whisper from orbit. The Tonga Arc has been building its chain of islands and seamounts for millions of years. Each volcano in the arc represents a place where water-triggered melting in the mantle above the subducting slab has produced enough magma to push upward through the overriding crust and reach the seafloor. Some of those volcanoes have grown tall enough to breach the surface and become islands. Others remain seamounts, mountains of volcanic rock that rise thousands of meters from the seafloor, but stop just short of the air. The chain grows slowly northward as the Pacific Plate moves, adding new volcanic centers over time in a record of magmatic activity stretching back through the arc's history. Cold, dense water from the trench floor eventually returns to the open Pacific. It does not stay at the bottom forever. Over centuries, it mixes with slightly warmer water, becomes marginally less dense, and begins a very slow migration along the deepest pathways of the abyssal plain. This water, cold, old, oxygen-rich from its original formation at high latitudes, eventually reaches the broader Pacific Basin and joins the deep global circulation. Nutrients that sank to the trench floor and were processed by microbial communities make that return journey too, rising over geological timescales to rejoin the surface ocean and become available to the organisms that live in the light. Nothing is entirely lost. The Pacific Plate will continue moving toward the Tonga Trench for tens of millions of years, at roughly 24 centimeters per year, about the length of a human hand, gained in every revolution of the Earth around the Sun. The plate covers significant distance over geological time. In 10 million years, it will have moved roughly 2,400 kilometers closer to the zone than it is today. The trench will have deepened slightly in some places, shallowed in others, shifted its position as the geometry of the collision evolves. The islands of Tonga will be different. Some uplifted, some eroded, some not yet born. The process is so slow that no living thing will witness even a small fraction of it. Yet it proceeds uninterruptedly, without regard for the world at the surface. Deep earthquakes along the Tonga slab produce seismic waves that pass through the entire Earth. When a major event occurs at depth, the energy it releases travels outward in all directions as compressional and shear waves. These waves refract as they pass through regions of different density, following curved paths through the mantle and core. Some of them arrive at seismograph stations on the opposite side of the planet. Stations in Scandinavia, in Antarctica, in the middle of other ocean basins, carrying a record of what happened deep beneath the Tonga region minutes earlier. The Earth uses its own body to transmit the message, and scientists on every continent are listening. The trench has accumulated its sediment layer by layer across a span of time that makes human history invisible. Each millimeter of sediment at the deepest part of the floor represents thousands of years. Each centimeter represents tens of thousands. A core sample pulled from the sediment and laid out on a table spans more time in a single meter of material than our species has existed. The scientists who study these cores mark their findings in millions of years. This layer from the Pliocene, this one from the Miocene, this one from before any primate had yet appeared. The floor is an archive of deep time, and it is still accepting new deposits, still recording what falls from above, still adding to its record one slow particle at a time. The ocean above the trench is part of a system that has been cycling water for billions of years. The water molecules now resting in the deep Tonga Trench have existed since the early Earth. They were here when the first life appeared, when the first fish evolved, when the first trees grew, when the continents arranged themselves into their current positions and rearranged again. In all that time, water has moved. From ocean to atmosphere, to rain, to river and back. But the molecules themselves persist. The water above the trench is ancient beyond any meaningful intuition. It is simply here now, as it has been in some configuration or another since before this planet had a moon. The Tonga Trench will outlast everything built by human hands. Concrete dissolves in seawater over centuries. Steel corrodes in decades. Plastic breaks into particles and disperses. But the Tonga Trench is driven by forces that operate on timescales of tens of millions of years. And the geological record suggests that subduction zones like this one persist for far longer than that, long after the last human structure has been absorbed back into the elements it came from, long after the surface of the Earth has been reshaped by erosion and volcanism and the slow rearrangement of land and sea. The process happening at this trench will still be ongoing. The plate bending downward, the slab sinking, the water rising, the volcanoes breathing, the floor collecting what falls. It does not need us to continue. It was never waiting for us at all. And so we arrive at the end of our journey into the Tonga Trench, the second deepest place on Earth, a scar in the seafloor more than 10 kilometers deep, driven by forces that have been operating since long before the first animal with eyes looked out at the world. We traveled through a trench carved by the fastest plate boundary on Earth. We visited water that has not seen daylight since before human civilization began. We found fish perfectly shaped by millions of years of slow pressure, microbes carrying proteins rebuilt by ancient chemistry, and a floor that records the history of the ocean in layers so thin they can only be counted in thousands of years. And you are part of this story too. The water in your body was here when this trench first formed. The atoms in your bones were forged in stars whose light predates the Pacific Plate itself. You are not separate from this deep, quiet, ancient world. You are made of the same material, shaped by the same long time. Let your breath slow now. Let the image of that dark, still floor settle somewhere beneath your thoughts. The trench is there right now, as it has been for tens of millions of years. Patient, dark, and complete. You don't need to hold on to it. Let it carry you gently down. Good night.